Hello and welcome to the next video in the series. In the previous video, we discussed about numbers. Namely, we talked about the natural numbers, which are a subset of the integers, which are a subset of the rational numbers, and finally we discussed the real numbers. But we did not discuss a set which contains all of them, being the complex numbers. Now, when talking about the complex numbers, a very important question to ask is, what problems do the complex numbers solve which cannot just be solved by the real numbers? Why do we need the complex numbers? Well, to answer that, let's take a look at a very familiar equation, which is the quadratic equation. Here's the general form of a quadratic equation, and with some rearranging, we can get it in a form which we should all be familiar with, being the quadratic formula over 2a. And there is a simple condition, being that a cannot be 0. Because if a is 0, then we do not have a quadratic equation. It is simply, it is simply linear, and x will just be minus c over b. Right? But there's also another condition, being the expression under the square root, which is the determinant, right? Well, the determinant, generally, we were taught that it has to be greater than or equal to 0, because our equation will look something like this. It will plot as a parabola. And a parabola, right? This equation is finding the x-intercepts of the parabola. And when the determinant is greater than 0, there are two distinct x-intercepts, because the peak, or the trough, sorry, of the parabola is below the x-axis. However, when we have that the determinant is equal to 0, we then have a parabola which touches the x-axis and has one x-intercept. But this one x-intercept is the same as these two x-intercepts going towards, so it is the limit as these x-intercepts come closer and closer together, and finally they come on top of each other, so it is two equal roots which are equal to 0. And now the final setup is if we have that the determinant is smaller than 0. So 4ac has a greater magnitude, positive magnitude, than b squared. In this case, we have a parabola which resides above the x-axis entirely. So where does this graph intercept the x-axis? From a theorem which is so important, which is called the fundamental theorem of algebra, every nth root polynomial has exactly n solutions. And here we have n being 2, we should have two solutions. We should have two x-intercepts, but here we don't have any. Well, let's continue observing this by going on to a simpler equation, being x squared plus 1 equals to 0. Well, this one is quite easy to rearrange. We have x squared is equal to minus 1. And okay, so in order for this equation to be satisfied, we have to have x being plus or minus the square root of a negative number. And there is no real number which has that property. I cannot multiply any two numbers to get a negative number. Because if I have two positive numbers, right, if I have a squared, I will just get a squared. And if I have minus a squared, I get a squared again. So there is no number which can square and become the square root of negative 1. Sorry, that can become negative 1. Well, let us for a second play devil's advocate and imagine that there is such a number, and let's call it I, and let's see where it takes us. So let us first look at a number line, right? Where here we have 0, here we have 1, here we have -1, and so on. We know the number line. And on this number line, let's place a point at 1, let's say. And now, when you multiply by a negative number, what's happening is you're essentially reflecting it onto the same value on the negative axis. Or you are rotating by 180 degrees. And if you multiply by -1 again, you're just going to end up, again, rotating anti-clockwise by 180 degrees. This is multiplying by -1. But -1 is just equal to I squared. So there should be a way to split this transformation up into two steps. Well, the obvious way to split it up is make it rotate by 90 degrees and then 90 degrees, right? That will make up 180. However, where is it landing? Because it's not landing in the real numbers, clearly, because there is no real number that satisfies this identity. Well, let's play further devil's advocate and let us assume that there is a separate number line housing the unit I, right? It's a completely separate number line. And because every single number on the real set can be multiplied by I, this imaginary line is the same as the real number line and contains the exact same numbers. It is just perpendicular to it. But what are the implications of this? Like, it's pretty cool, but what exactly can we do with this? Well, one thing that we can do is we clearly see that in this space, multiplying by I acts as a rotation by 90 degrees. That's pretty cool. However, what about adding a real number and a complex number? Well, this 1 plus I doesn't really have a neat answer, because this is a real number and this is an imaginary number or a complex number, right? Okay, it is an imaginary number. And just like in the first video where we had apples and oranges, where if we have 2 apples and we have an orange, even if we add them together, we don't have 3 of something other than fruits. But we cannot just add these 2 sets together. They're distinct. And just like with them being fruits, we can now just say that these are complex numbers. This whole thing, a sum of a real number and an imaginary number, makes up what we shall call a complex number. And this complex does not stand for complicated, by the way. It is like an apartment complex. It is an arrangement, rather, of a real number and an imaginary number. Now, this complex number, how do we place it on this number line? On these axes, sorry. Well, if we take 1 plus I, we can take lines, right? Just like in 2D, right? Where we have y is equal to I and x is equal to 1. And let's plot a point here. And then let's take some green and let's draw a vector from the origin to that point. And now this vector can be placed, any addition of real and complex numbers mean I can place this vector anywhere in 2D space. So I essentially have a span of an entire 2D plane. And this 2D plane is the complex plane. And now, because I have a vector, I can not only define it in terms of what's known as rectangular coordinates, which is this sum right here, but I can also define it in terms of its magnitude and the angle it makes to the positive real axis, just like with standard vectors. And here, now we have that this also can be alternatively represented by a magnitude and an angle theta. But what is this magnitude? Well, it's a unit square, right? So this means that it has a magnitude of √2, and the angle, again, unit squares, pi over 4, or 45 degrees. Now we have two different ways of representing vectors, but there's also a further way when looking at the magnitude and angle, right? Where we'll represent the complex number as the letter Z, right? And let's define it as a function of magnitude and of angle. And now we have defined polar coordinates in our complex plane. But from these polar coordinates, this means that our complex number, we can take the real part of Z is equal to, we have r times cosine theta. So here we have r cosine theta, and we have the imaginary part of Z is, let's look at it, we have r and we have sine theta, right? We have r sine theta, simple geometry. But now if we want to combine these, what we get is that Z is equal to now r, we can just factor it out, and we have the real part, which is cosine theta, and we can add the imaginary part. But in order to add it, again, we want to multiply by I, and we have I sine theta. But now let's take a step further in, right? And let's play around, and let's, I don't know, take the derivative, the partial derivative, right, with respect to theta of Z, right? And for our intents and purposes, let's just imagine that r is 1, right? Because, again, our result, we can just multiply it by r. So, yeah. So here, what we have is cosine theta derived is minus sine theta. And then here, derive this is plus I cosine theta. And let's put everything to I, so minus 1 is I squared sine theta plus I cosine theta. And let's factor out an I and put cosine first. So we have I cosine theta plus I sine theta. And now what we have is we have I times Z. For some reason, the partial derivative with respect to theta of Z has given us a constant number I times Z. Now, what functions do we know that have this property, where if we derive them with respect to x, right, a function f of x, will give us some constant times f of x. And normally we would say this is part of the real numbers, but now we have expanded, so this is part of complex numbers. It can take on any value, right? And we actually know something, a function which perfectly fits this description, and that function is f of x is equal to e to the kx. Because when you derive this, right, this becomes k e to the kx. Now substituting k for I, we get I e to the ix. right? And if we make x theta, as I said, so now if I take the derivative of, let's call this w, right? So w of theta, what I get out is I times w, right? And it's the exact same thing we had with z. So now I can multiply r into this, and I can make it r times I omega, and I can multiply this, and I get the same thing. So what is being said is that z is equal to w, or cosine of theta plus I sine theta is equal to e to the I theta. Now, this is a very strange property, but it is a profound property. Somehow, we now, from accepting that the square root of -1 might have a numerical answer, just not in the real numbers, we have gone from having a problem with algebra and now to finding a link between sinusoids and exponentials, where sinusoids are great at explaining angles and anything to do with circles, whilst exponentials are very useful in all calculus because, again, it is its own derivative. This is a massively important identity. And in fact, we can now define that cos theta, right, is equal to e to the I theta plus e to the minus I theta, because cosine is an even function. It will not change, but sine is an odd function. So we'll have plus I sine theta minus I sine theta, right? So we'll just get 2 cosine theta, so we just divide by 2. And same thing with sine of theta, except the sign is different, so we want to subtract, right? So now cosine gets cancelled out, but now we have 2i sine theta, which will mean we just have to divide out by 2i. And now we can define the sinusoids in terms of complex exponentials. Now, these formulas might seem to be just a mathematician having a bit of fun, right? But actually, the usefulness of these identities is unprecedented, especially in the field of electrical engineering, which we will discuss over the course of the next 2 videos.